So let's practice some questions involving that relationship. So we have, let's see, show that the following equations are true by simplifying the left side. So we want to do a simplification of this expression to see if it ends up matching this one. If it does, then the equation is true. So we're going to rewrite this whole fraction. Sine of theta, I like sine of theta. That's pretty simple. Cotangent of 90 minus theta. Cotangent of 90 minus theta, that's the same as the tangent of just theta. And I'm going to work my way to the right here. All I'm doing is just writing these fractions in a new version, trying to get down to the cosine of theta. So sine of theta, I'm just going to rewrite this over. Now tangent of theta is the same as sine of theta over cosine of theta. And if you're dividing by a fraction, you just multiply by the reciprocal. So that's equal to sine of theta times the reciprocal of sine over cosine, which is going to be times cosine of theta over sine of theta. Now, sines cancel, and I'm just left with cosine of theta, and I got a match. And that demonstrator showed that that equation was true because the left-hand side simplified to be cosine of theta. Next one, secant of theta tan. Okay, so we're going to try to convert this to functions we like. So secant of 90 minus theta is going to be the same as cosecant of theta. Tan of theta is the same as sine of theta over cosine of theta. Put a 1 over 1 there. And let's see, cosecant, I happen to know that cosecant is the reciprocal of sine. So this is going to be, working my way over to the right, 1, that really was ugly, 1 over sine of theta times sine of theta over cosine of theta. The sines cancel, and I'm left with 1 over cosine of theta. Now one last step, I happen to know, again, that the reciprocal of cosine is the definition for the secant. So this is equal to secant theta. And I'm done. I've showed that the left-hand side simplifies down to be something equal to what's on the right, so the equation is true. Pythagorean identities. So I've got a picture here. Should look a little familiar. This is the first quadrant of a unit circle. So we have a ray, which is the radius of the unit circle. It has a length of 1. And we have these segment lengths that you found in a recent application problem, and they're identified. Sine is the y-coordinate of this point here, so the y-coordinate is going to be equal to the length of this side of this right triangle here, and the x-coordinate of this point is the same as the x-coordinate here, which means that the x-coordinate of that point is the same as the length of this side. So since this segment that we drew in here was perpendicular to the x-axis, I know this is a right triangle, this is a right angle. So this right triangle should observe the rules for the Pythagorean theorem, which is to say that this leg squared plus this leg squared should equal this leg squared. And that's what we've done here. We've got the vertical leg here, the sine of theta. We're squaring it here. We have the horizontal leg here, squaring it there. If we add those together, we should get something that's equal to 1 squared. 1 squared is just 1. Make this just a scooch larger. So, doing something similar with tangent and secant. So involving the tangent and secant, we're going to be looking at That's hardly visible. Let's try this. This right triangle here, because the hypotenuse is secant. One leg is tangent, and the other leg is 1. So we could write out Pythagorean theorem for this triangle and say 1 squared plus tangent squared theta equals secant squared theta. Just to be sure. 1 squared plus tangent squared theta equals secant squared theta. And I think I've mentioned this before. This is a piece of notation. If I say tan, that's the name of the function, squared of theta, that really means, and I'll rewrite this in that form. So 1 squared is 1 plus tangent theta all squared equals secant theta all squared. So when we write, if we want to take this tangent of theta, take the result of tangent of theta and square it, likewise secant of theta, take the result of that and square it, instead of writing this out with all those parentheses, we use this other notation. We write the name of the function raised to the second power and then put the argument afterwards. Tangent squared theta. That's just a piece of notation that means this and this respectively. All right, cotangent and cosecant. So cotangent is this leg, the other leg is 1, a hypotenuse is cosecant. So we can write out, again, Pythagorean equation for that. 1 squared plus cotangent squared theta, here's that notation again, equals cosecant squared theta. Remember, of course, as you go and use this, 1 squared is 1. Bingo. So, well, what does this do for us? Well, if you see an expression that's like 1 plus cotangent squared theta, you could say, I remember trig functions when they're squared, they might appear in this Pythagorean identity. If I see a 1 plus cotangent squared theta, I can replace that with cosecant squared theta. Likewise, 1 plus tangent squared equals secant squared. And you can rewrite these in various other ways too. These are very rearrangeable. For example, you could take this and write it as 1 equals that is also true. All I did was take this equation and perform basic algebra on it. Just rearranged it using rules of algebra. I subtracted. Why did I write that? It's supposed to be cotangent. Shh. Sorry about that. I subtracted cotangent squared from both sides and rewrote this as 1 equals cosecant squared theta minus cotangent squared theta. So, if this ever showed up in your math, your algebra somewhere, you could say, oh, I remember that. That's just 1. And so that's how you get some really amazing simplifications. Okay. Now I have some more examples to try. Now, these are puzzles in a way, and the only really good advice that I have for you is try things. If you do things that are valid substitutions in valid algebra, you can't go wrong. There are many different paths to simplifying these things, and so really what we're doing again is showing that they're true or simplifying. And there are often many different paths to follow, and you don't always do the right thing the first time. It's just a matter of practice. So far, we haven't seen any identities that involve 1 minus cosine of b, or 1 plus cosine of b. We have seen one involving sine squared of b. That was up here. This Pythagorean identity involved a sine squared. So, but that doesn't help us much because nothing good is on the left-hand side. So what I'm going to try doing is maybe multiplying, foiling these two together. Let's see what happens. So I'm going to foil them. The first product is going to be 1. The outer product is cosine of b. The inner product is minus cosine of b. The last product is minus cosine squared of b. So this is the left-hand side of the equation that I've rewritten. And it doesn't look any simpler. However, cosine of b minus cosine of b, those two cancel each other, and we get 1 plus. No, we don't get 1 plus. We get 1 minus cosine squared b. And the question is that equal to sine squared b? Well, we could rewrite the left-hand side of this, or we can continue doing algebraic operations until we get something that is undeniably true. For example, I can add cosine squared b to both sides, and I'll get 1 equals, because that's going to cancel that out, sine squared b plus cosine squared b. And at that point, I'm actually good, because 1 equals 1. Why does that equal 1? Well, sine squared b plus cosine squared b, sine squared theta plus cosine squared theta equals 1. And that's always true. You can count on that. So this is really an awesome thing to remember, that sine squared plus cosine squared always equals 1. And if you don't believe it, try evaluating sine squared b plus cosine squared b for different values of b. Use your calculator. Go wild. It actually works. Next up, we're going to look at number 6. Secant squared a. I'm thinking this might be familiar, so I'm going to go peek upstairs. There is a Pythagorean identity that involves secant. And if I took this Pythagorean identity and did some rearrangement by, let's say, subtracting 1 from both sides, I would get tan squared theta equals secant squared theta minus 1. Well, secant squared theta minus 1 is exactly what I'm dealing with down here. And I've just shown myself that secant squared theta minus 1 is equal to tan squared theta. So let's go rewrite this. This is cosine squared a times tangent squared a. I got balled up trying to write a theta. A equals sine squared a. Let's see, how's this working out? Well, tangent is equal to sine over cosine. So this becomes cosine squared a times sine squared a, because we're just squaring numerator and denominator. And explain everything is losing me here. Sine squared a. Now, cosine squared over cosine squared, those cancel. And I'm left with sine squared a on the left and sine squared a on the right. It works.